Integration by substitution. So we know by the fundamental theorem of calculus that, the first step to evaluate a definite integral is to find a primitive function of the integrand. Okay? But there are functions that we don't have the tools to find primitives for. For instance, take a look at this. Primitive of 2x square root of 1 plus x squared dx. Up to this point, we don't know how to integrate this function, 2x square root of 1 plus x squared dx. Okay, so we're gonna develop a tool in this section that allows us to handle this situation. Before we start, let's recall the following. If you have a function u, a function of x, and which is differentiable, then du over dx is equal to u prime, right? This is what it means. Du over dx is equal to u prime. And by definition, we define the differential of u to be u prime times dx, right? And we thought about it as multiplying, like cross multiplying. Okay, so du is equal to u prime times dx. For example, if u is the square root of x, find du. Well, we want to find du. Du is u prime dx, right? So du is u prime times dx. The differential of u is equal to the derivative of u times the differential of x. What's u prime? What's the derivative of square root of x? Is 1 over 2 square root of x, right? dx. So what's du? Is 1 over 2 square root of x dx. Next situation. If u is x to power 4 plus 2x, find du. Well, again, by this definition, du is u prime times dx, and u prime is the derivative of this function, so it's 4x cubed plus 2 times dx, right? Okay, one more time. If u is 1 minus 4x squared, find du. Well, du, the differential of u is equal to u prime dx by the definition above, which means the derivative of this u is how much? Derivative of this u with respect to x. This is minus 8x dx, right? Okay, so the differential of u in this case is negative 8x dx. All right. The substitution rule. Let's read this theorem. It says the following. If you have a function u that's a function of x, g of x call it, that's differentiable, whose range is in an interval I, and f is continuous on that interval I, then you get this. You get this property. The primitive of f gx times g prime x dx is equal to the primitive of fu du. Let's prove this. Since the function f is continuous on I by design, there must exist, by the fundamental theorem of calculus part 2 here, you can construct a function capital F on I such that the derivative of f is equal to little f. So what I'm saying is, because f is continuous on I, you can find a primitive function of little f. Let's call it capital F. As such, by the chain rule, the primitive of this is equal to that. Why? Go back. Try to differentiate this function with respect to x. If you differentiate this function with respect to x, what you're gonna get is that guy, right? You're gonna get that guy by the chain rule. Am I correct? Remember, chain rule is derivative of the outer with respect to the inner, right, times the derivative of the inner with respect to its own variable. So this is true then. Let's call this equation star. Now, if we make the substitution u to be g of x, so if you call g of x to be u, then from equation star, from this equation, we can write the following. you start here, is equal to capital F of gx plus c, but remember we just said let u denote g of x, so we get this to be u, so we get f of u plus c. Okay, and that last expression is a primitive for the function f prime u du, right? So this is a primitive of the function f prime. If you think about the variable being u now, if you think about the variable being u, f of u plus c is primitive function of f prime of u, correct? Again, I'm talking about du here, so this prime means you are differentiating with respect to u. Okay. All right. And because f prime is little f, that thing becomes primitive of f prime gx g prime x, like this, dx, and this becomes little f u du. Makes sense? So you get that. And this is actually the conclusion of the theorem. This completes the theorem, the substitution rule, right? This completes the substitution rule theorem. Very good. So we get this formula then, and let's read this comment. So in this rule, in this substitution rule, notice that you can think about, if you think about u as being g of x, right? If you think about u as being g of x, then what can you say about du? Well, if u is g of x, du is g prime of x dx, right? So du becomes this, no? You agree with me? So if you think about u as being g of x, then du, based on the discussion above, beginning of the section, du is g prime of x dx. Okay? So a way to remember the substitution formula, is to think of dx and du in the formula of the theorem above as differentials, like we just discussed at the beginning of the section. Okay? So therefore, the substitution rule tells us it's permissible to operate with dx and du after integral signs. After integral signs, this stretched s, right? This integral sign, stretch s. You can think about du and dx as being what? As being differentials. All right? Let's do some problems. Let's start by the following. Let's start with the one that we just talked about at the beginning of this section. So primitive of 2x square root of 1 plus x squared dx. Okay? So it all comes down to choosing an appropriate substitution. Right? This is what the formula is about. It comes down to finding an appropriate substitution u for g of x. Correct? This is what the formula says. Okay, so how about we think about this as, in order to set the stage for the choice, how about we think about this as 2x plus 1 plus x squared to power half dx. Okay, which is the same as 1 plus x squared to power half times 2x dx. What I'm doing is just reversing the order here, right? A times b is b times a. So 2x times that is the same as that times 2x. Okay? And I want you now to contrast this with the formula. I hope they can fit on one screen. Let's try. Okay, look. I want you to contrast this with the formula. So you have a function of u, and here you would hope to have du. Do you see who should be the u then? Do you see who should be the u? How about if you think about x, or 1 plus x squared to be the u? If you think about 1 plus x squared to be the u, this would be du, right? One more time. If you think about 1 plus x squared to be the u, du would be the derivative of this, which is 2x dx, correct? So we get this. So if we choose u to be 1 plus x squared, that guy, this guy here, which is 2x dx, becomes du. Okay? All right, so let's do the following substitution. Let's let u to be 1 plus x squared, and as such, du, the differential of u, becomes the derivative of u, which is 2x dx. Correct? The derivative of u, which is 2x dx. We just talked about this at the beginning of this section. Very good. So I'm using that thing here, and then we get, by the chain rule, not the chain, sorry, my bad. I mean the substitution rule, right? So this is substitution rule. By the substitution rule, we get that this is equal to u to power half. This becomes, because I'm talking about 1 plus x squared as being u, right? 1 plus x squared as being u. This becomes then half of u, not half, u to power half times, what's 2x dx? Well, 2x dx is du. So this whole thing then becomes du. Correct? And look at this. Look at this here. Do you recognize this? Do you recognize something to power n d of that thing? At the time we called it x. This is a couple sections ago, right? Primitive of xn dx, primitive of tn dt, primitive of un dn, right? Primitive of bullet to power n d to the bullet. This is the same as the bullet to power n plus 1 divided by n plus 1 plus a constant of integration, obviously as long as n is not -1, right? So for all n that's not -1, correct? So that's what's gonna happen here. That's what I'm gonna be needing here, because this guy here looks like that, right? Looks exactly like this. So that becomes based on this formula, which has to do with the power rule, remember? Anyway, so we get u to power half plus 1 over half plus 1 plus a constant of integration. Correct? Okay, and what's half plus 1? Half plus 1 is 3 halves. Dividing by 3 halves is the same as multiplying by 2/3 plus a constant. Okay. And the question was given in terms of x, so I have to return the answer in terms of x. U is an auxiliary thing. U introduced it to the problem. So let's give back the answer in terms of x. What was x for us? Sorry, what was u for us? It was 1 plus x squared. So this becomes 2/3 times 1 plus x squared to power 3 halves plus a constant of integration. Correct? So we used an appropriate substitution to actually integrate this, because we didn't know how to integrate it except if we find an appropriate substitution, and we did. This is one of them. And as such, we used the substitution rule and we applied it. Once we applied, we got back to a stage where we can handle them using previous techniques. Okay. In this case, it was this formula. Don't worry about, don't remember these with the letters X and etc. Just remember them in the format of bullets in some sense, because anyway, it becomes, if you remember it with X all the time, it kind of becomes misleading. Okay, so anyway, so whatever that thing is, it's, as long as they are the same thing, you can apply this formula, right? And you get that. And in this case, I have it. You see the U, you see the U, so that U is the bullet. And we have this setup. The n is not -1, it's half in this case, it's not -1. And you apply it, and then from there on, once you integrated, here I integrated, right? I applied this is integration here. I integrated, I found the primitive function, and then go back to what U means. So that U was an auxiliary thing to simplify the problem, to put me in a context of a primitive, to give me an indefinite integral, which can be easily handled by previous techniques. Okay. So the idea of the substitution rule is to transition, by an appropriate substitution, to transition from a complicated integral to a simplified one, okay, a simpler one, let's say, like we did here, where all techniques can apply. Okay. All right, let's do another one. How about the following, part 2? The integral of x cubed cosine x to power 4 plus 2 dx. Look, if try, obviously you should try to stop the video and try on your own first. And when you finish, hopefully you are successful, and then if not, you can learn from the way I'm looking at it. Look, you see this guy? I'm gonna think about this as U. If I think about this as U, if you take the differential of this guy, if you take the differential of U, you get 4x cubed, right? 4x cubed dx. And I have the x cubed here. I don't have the 4, I agree with you. But look, the 4 is not a big deal. The 4 can be, I can introduce it and simplify it, right? I can introduce it and simplify it. So, and as such, this becomes my U, and this 4x cubed dx, 4x cubed dx is my du, okay? That multiplicative constant is not a big deal. So we should always try to choose an appropriate U to be a function in the integrand whose differential also occurs. You see the differential of x4 plus 2? It occurs, x cubed dx, except for a constant factor. And that constant factor can always be introduced if needed, right? Can always be introduced if needed. In this context too, if the 2 didn't exist, I can always multiply by 2 and divide by 2. No problem. Correct? So one more time, let me say this again. So we always try, this is the challenge. We always try to choose an appropriate U substitution to be some function in the integrand whose differential also occurs within that integrand, except for a multiplicative constant. All right? Very good. So in this context, as we said, if we take U to be x to power 4 plus 2, the differential of U is 4x cubed dx, right? 4x cubed dx. I see x cubed dx here. I see x cubed dx. Okay? Let me actually rearrange it so you see it better. This is the same as cosine of x4 plus 2 x cubed dx. Correct? You agree that this guy and this guy are the same? You agree that they are the same? The differential of u can be found here, as just discussed before. The differential of u can be found here except for a multiplicative constant, right? That constant factor, you can always introduce it, no problem. But the big deal is the the I mean the x cubed dx is already here. Okay. All right. As such, what do we get? So we get what? I'm using this package. So you can multiply by 4 and divide by 4, or you know what? How about instead of multiplying by 4 and divide by 4, what I'm saying is instead of putting a 4 here to make up for the du and divide by 4, right? I can do so. How about actually we do the following? How about we solve x cubed dx in terms of du? This doesn't mean that this guy x cubed dx is du over 4 or 1/4 du. So if you divide by 4 here, 1/4 du, isn't it x cubed dx? Correct? And this guy is the same as this guy, right? I mean, it's still the same guy. Makes sense? So 1/4 du is still x cubed dx. It's right there. So now if we go back to this, this integral becomes the integral of cosine of this guy, which we chose to be u. You cannot write here x cubed dx. You cannot have a mixture of variables, u, x, because you're integrating here with respect to x. You cannot have u, right? You have to have homogeneity of the variable. So if you have u, you should have du here, okay? And adjust appropriately. So this is cosine of u times this guy. What's this guy in terms of u and du? This guy is 1/4 du. Just talked about it. This colored thing, this highlighted thing, is 1/4 du, right? Does it make sense? And this is the same as we just talked about over here, 1/4 cosine mu du. Remember when I told you you can introduce a 4 here and divide by 4, right? And this whole thing now becomes the du, right? You see, we get this whole thing as my du, and the 1/4 is gonna occur outside. So if you didn't want to do it this way, you can solve for x cubed dx. You can solve for x cubed dx, and you solve it in terms of u and du, right? So either you do it as such, or you do it with exactly as we did it in these two steps here. So we transitioned from an integral that has only x. Look, everything here is in terms of x, right? And now everything here is in terms of u. So we transitioned from this to that. But look, this is easy. Primitive of cosine bullet d bullet, right? Primitive of cosine. We know the following. Primitive of cosine x dx. What is it? Primitive of cosine x dx. Isn't it sine x plus a constant? Remember this? But what's so special about x? It's just a dummy variable. How about we think about it as an asterisk? Correct? That's my point. So this looks like primitive of cosine asterisk d asterisk is sine of asterisk plus c. Don't you have the asterisk here? You see the u? That's the asterisk. You see, this is the same one as this, so I can apply it, no? Okay, so we did an appropriate u substitution to transition this complicated looking integral to a simpler one, where all techniques, as I said, earlier can apply. Okay, and once this kicks in, we're done with integrating. We're done with integrating. Plus some constant, right? So you can tell me, oh, I should multiply the constant by 1/4, but this is arbitrary. If you multiply an arbitrary constant by 1/4, that remains an arbitrary constant. So how about calling it C? If you don't, I mean, if you don't want to have the same C, how about K? Okay, so K is 1/4 of that C. Okay. All right. So we're done with integration. You see, no more integration symbol, no more of this S, this stretched S, no more of this. So we're done with integration. And now let's go back to what U means, since U helped us to integrate. Now we're done with integration. Let's go back to what U means. Well, what U means is x to power 4 cross 2. Correct? Look, if you want to check your work, you can always differentiate this, and you should get back the integrand. Correct? If you differentiate, this is what this means. What we just found means the following. We found a primitive of x cubed cosine x4 plus 2, and the a primitive, or any primitive, is going to look like this: 1/4 sine of x4 plus 2 plus a constant. If you want to recheck your work, if you're more comfortable to differentiate than integrate, how about you differentiate this guy? You should get back exactly this, right? Try it. If you differentiate this guy, it's 1/4. What's the derivative of sine of some function? By the chain rule, it's the derivative of the guy inside, which is 4x cubed, right? So 4x cubed divided by 4 is x cubed. So we're back to this, times cosine of x to power 4 plus 2. So we get exactly this integrand. So this is correct. Okay. Let's do another one. How about part 3? About integrating cosine 7x dx. How about we integrate this? What do you think the appropriate choice of the U substitution? Here I cannot use, let me highlight this. I cannot use this. I cannot use it because if you think about this, this is a bullet. If you think about this as a bullet, you don't have the bullet here, right? If this is the asterisk, 7x is the asterisk, I don't have this as an asterisk, correct? They're not the same. They're not the same. That's my point. Over here, they were the same. This is why we applied it. U. Over here, I have 7x. I don't have 7x here. Okay. So, what would be an appropriate U substitution? Please stop the video and think on your own first. I'm gonna take U to be 7x. And as such, du is, what's the differential of u? It's the derivative of this with respect to x. What is it? 7 times the differential of x. You got that? Okay. So that's my u, and this becomes dx. I don't have, it's dx, but look, this, I don't have a 7, but 7 is a constant factor, right? It's a multiplicative constant. You can always introduce it and divide by this constant. Make sense? So this is then equal to primitive of cosine u times, as we said, multiply by 7, divide by 7. If you don't want to do it this way, how about we do it as we did it above? About here, we solve for dx. What's dx? What's dx in terms of du? Isn't it 1/7 du? Isn't it 1/7 du? Correct? Dx is 1/7 du. Divide both sides by 7. That's what I'm saying. Because you want to write everything here in terms of u. Everything has to be written in terms of u. The 7x is the u, and the dx has to be written in terms of u, and it's differential. Well, it happens that 7 dx is du. So what's 1 dx? It's 1/7 du. So instead of dx, I can replace it by 1/7 du. Make sense? So this becomes then 1/7, which is a pure constant, push it outside, primitive cosine u du. Alright, now I can apply this property because I have the asterisk and the asterisk. They're the same now. They're the same now. So this is then equal to 1/7 sine of the asterisk, which is in this case u, plus a constant. Alright, and what's u in our context? It's 7x. So we get this, correct? If you want to check your work, differentiate this, you should get cosine of 7x. 4. How about primitive of the square root of 2x plus 1 dx? Again, please stop and try on your own first. The way I'm gonna do it, how about we take u to be 2x plus 1. If you take u to be 2x plus 1, this forces du to be 2dx, right? Why? Because du, the differential of u is the derivative of u. Now what's the derivative of u? Is 2, right? Times dx. So we get that. And then this integral becomes what? Primitive of square root of 2x plus 1, which we are thinking about it as u now, dx. We don't want to write anything in terms of x anymore, right? Just in terms of u and du. What's dx? What's dx in terms of u and its differential? Well, dx is 1/2 du, right? Solve for dx here. Solve for dx. Don't you get half du is dx? Right? If you solve for dx, this is a constant, this is a constant factor here. So you multiply by 2. If you want to get rid of that guy on this side, divide, right? Alright. So this is what's going on here. And what we get is instead of dx, I can write half du. Instead of dx, I can write half du. Right? Because I don't want to write anything here in terms of x anymore. It's just in terms of u and its differential. This is why we're getting rid of this dx to write it in terms of u and its differential. And the way it turned out to be, it's that this is half du. Okay, so that's half primitive of square root of u du, which is half times square root. Let me erase it. Square root means power half, right? Square root means power half. And if you reapply this principle, now we have n to be half. Actually, we did this before. It's the same one. So it's gonna be 2/3 u to power 3/2, right? Okay. So it's gonna be 2/3 u to power 3/2. Since we've done it, I'm just copying it. Plus c. Makes sense? And that's equal to 2 and 2 cancel. 1/3 u to power 3/2. But what's u? It's 2x plus 1, right? To power 3/2 plus c. Makes sense? And if you would like to simplify the writing, because here 3 is bigger than 2, so I can simplify that. This is the same as 1/3 2x plus 1 times the square root of 2x plus 1 plus a constant. A different way, I mean, we can do this in a different way actually. Okay, we can do this one in a different way. Let me show it to you a different way, and I hope someone else did it. How about we take the u, the substitution, to be 2x. Actually, how about we take the whole thing as being the substitution? Over here, we took the substitution just to be the radicand. How about we take the whole integrand to be the substitution? Let's see what happens. So a different approach. So different substitution. How about taking v now to be square root of 2x plus 1? What's dv then? What's dv? You gotta use chain rule here. It's v prime. dv is v prime dx, right? Okay, what's v prime? We're gonna use chain rule for this. We're gonna use chain rule for this. It's gonna be half times the 2x plus 1, correct? Half times 2x plus 1 to power half minus 1, so minus half, times the derivative of 2x plus 1, which is 2, times dx. And this is only chain rule here, right? This is chain rule here. Okay. All right. And that's what? And that's what? This is the half times 2 is 1. So this becomes 2x plus 1 to power negative half dx. You hear that? Okay, so back to the integral. So the integral that we had, which was square root of 2x plus 1 dx, is equal to, we call this whole thing v, right? We call this whole thing v. We call this whole thing v, yes. Okay, times dx. I don't wanna see here dx anymore. It should be in terms of v and dv. What's dx in terms of v and dv? Well, what did we find for dv? Let me make some room for us. Look. You see dv? We found that dv is this, right? dv is this. And which means, take a look at this. This guy means 1 over 2x plus 1 to power half. Agree with that? dx? You agree that this minus here means the reciprocal of the guy? So we get that. And you recognize this guy here? Who's this guy? Who's this guy? Isn't it the v guy? Isn't this guy v? This guy is v, right? And then dv, then this means that dv is 1 over v dx, correct? 1 over v, because the guy downstairs is v now. Dx, I don't know why I wrote this dv. This is dx, right? dx. Okay, and so what is dx then? So dx is v dv, right? Solve for dx. Solve for dx. So dx is, solve for dx here, is v dv, multiply by v, right? Is v dv. Agree with that? If 1 over v dx is dv, so dv times v is dx, right? So we are able to write dx in terms of v and its differential. So back down here, dx, it's that guy, right? Which is v dv, So instead of dx, I can write v dv. Make sense? And you see now everything is in terms of b. No more x. No more x. And this looks good. This is primitive of v squared dv. Correct? This is primitive of v squared dv, which is primitive bullet to power n d bullet. That's what? That's the bullet to power n plus 1 divided by n plus 1 plus a constant, right? So what am I using? I'm using this property. I'm using this. N in this context was 2, certainly is not negative 1, so I can apply it. Okay. Very good. So we get this, and this is the same as 1/3 v to power 3 plus constant. And what's v for us? So what is v for us? It means this, correct? So v is the square root of 2x plus 1 cubed. Make sense? Plus a constant. Plus a constant. Okay? And this is equal to 1/3. That means what? This means what here? This means that guy times itself 3 times. Well, 2 of them are going to give you 2x plus 1 times square root of 2x plus 1 plus a constant. Very good. Next. How about part 6? Sorry, not part 6, part 5. Okay. So the integral of x over square root of 1 minus 4x squared dx. Okay. If we take 1 minus 4x squared as my u, substitution as my u, the derivative the derivative of this, or the differential of u, is gonna be negative 4 times 2x dx, so negative 8x dx. And you see the x dx upstairs? X dx. So if you throw in a negative 8 here, divide by negative 8, so it's a constant factor, it looks like this would be promising substitution, correct? So I'm going to substitute 1 minus 4x squared by u. As such, du is equal to minus 8x dx, as we just said, which means the x dx is negative 1/8 of a du. Correct? So that's what's going to happen here. That's what's going to happen here. And then what do we have? We have the primitive of the guy downstairs, as we said, that's the u to power half. Okay? So that's u. Alright. About square root of u. Just to be not to confuse you, because 1 minus 4x squared is the u, right? So the guy under the umbrella is the u. So I get the umbrella of u, right? And then x dx upstairs, x dx, what's x dx? Let me color it for you. The x dx here, which is this, I can replace it by negative 1/8 du, right? So that guy upstairs becomes negative 1/8 du. Make sense? Alright. So then what do we get? Is this an easier integral? Minus 1/8 is a multiplicative constant. The integral of du over square root of u, right? So technically I should write 1 over du. Do you agree with me? But people write du over square root of u as an abbreviation of this. Okay? So as an abbreviation of this, people erase this part and write du over square root of u. Okay, this is an abbreviation of what you just saw just a moment ago. Alright, and is this easy? Maybe not yet. Square root of u downstairs means u to power negative half upstairs. Correct? Du. Alright, that's better. I can still apply this bubble that's refer to it multiple times at this point, right? This one. The n in my context is -½ and I have the same bullet here and here. So I can apply. Certainly -½ is not -1, so I can apply. Correct? You see the same bullet? It's the same bullet. This one. Correct? Alright, so this is then -1/8 times u to power -½ plus 1 divided by -½ plus 1 plus a constant. Okay, and what's -½ plus 1? Isn't it 1/2? And dividing by 1/2 isn't the same as multiplying by 2? So that becomes -1/8 times 2 times u to power 1/2 plus a constant. Yes? So that becomes -1/4 of u to power ½ plus a constant, which is -1/4 of u to power ½. What's u? U was 1 minus 4x squared to power ½, which means square root of that guy, plus c, right? This means square root of 1 minus 4x squared. This means square root of 1 minus 4x squared plus c. But this is a good representation of the answer. If you want to try to see if your work is correct, differentiate this primitive, differentiate this guy. You should get this integrand, right? Okay. Last one before we go to the next concept. So how about the primitive of the square root of 1 plus x cubed times x to power 8 dx? Okay. All right. Please stop the video and think about this one. This is the hardest up to this point. Okay, please take a few minutes to think about this one. My approach is as follows. I'm gonna take q to be 1 plus x cubed. As such, du becomes 3x squared dx, right? Du is u prime dx and u prime is this. Okay, it looks like, oh, we didn't reach x to power 8. Well, this is the same as primitive of square root of 1 plus x cubed, and I can think about x to power 8 as being x to power 6 times x squared dx. Agree with this? Hopefully now you see the x squared dx. It's right there. That guy and this guy are the same. But x6 is what in terms of u? So far, I can represent this in terms of u. Agree with that? This is square root of u. I can represent this in terms of u or du, right? Which is d over 3, correct? This guy is du over 3. But what is this guy in terms of u? U is 1 plus x cubed. What is that? Well, this is the same thing as the integral of square root of 1 plus x cubed. The x to power 6 is the same as x cubed squared, no? X to power 6, isn't it x cubed squared? Isn't x cubed times itself x to power 6 times x squared dx? Aha, now I can see it. X cubed, I see x cubed in terms of u. It's u minus 1, right? X cubed is u minus 1. Agree with me? So x cubed is u minus 1. So I can write then x to power 6, which is x cubed squared. I can write it in terms of u. It's u minus 1 squared. Agree with that? Okay. So this becomes equal to, now I can inject this discussion here. I can inject it here. This is the u substitution part. So that becomes the square root of u, because 1 plus x cubed is u, the square of x cubed, and x cubed is u minus 1, and x squared dx is 1/3 du, right? 1/3 du, correct? X squared dx, this part, is 1/3 du, right? So you see this integral now? Everything is in terms of u. Everything is in terms of u. And this is an easy integral because you can square that guy, and this is a polynomial times square root of u. You can handle it. Correct? So this is equal to the integral of square root of u minus 1 squared times 1/3, it's a constant, multiplicative constant, du. And as I said, you can, u minus 1 squared, that's the same, this is a polynomial. What's u minus 1 squared? It's u squared minus 2u plus 1 du, right? Correct? If you FOIL this out, u minus 1 squared, you get this. Okay? And that's 1/3 times the square root of u, the integral of square root of u squared. What's square root of u squared? Multiply these guys. You add the powers, right? This is square root of u times u squared, which means u to power 2 plus half, and u to power 2 plus half is u to power 5 halves, right? Correct? 2 plus half is 2, is 4 plus 1, so 5 over 2, right? Minus square root of 2 times 2u is 2 times, what's square root of u times u? Is u to power half times u. U to power half times u is u to power 3 halves. And the last one is square root of u times 1, so it's square root of u, which means u to power half du. Correct? And now you can integrate this. Now you can integrate this easily. This is again that formula that we've been alluding to over and over, right? So let me take you back to it. I'm talking about this one. I'm talking about this one, right? Each one of those integral that we have below are exactly of this form, where the bullet is the u, but we have different ends, correct? So what do we get? We get u to power 5 over 2 plus 1 over 5 over 2 plus 1 minus 2 u to power 3 over 2 plus 1 over 3 over 2 plus 1 plus u to power 1/2 plus 1 over 1/2 plus 1 plus a constant of integration. Correct? Let me erase this part. Plus a constant of integration. Very good. All right, so now what? Now you just do the algebra and replace u by what it means for us, right? So that's 1/3. What's 5 over 2 plus 1? That's 7 over 2. That's 7 over 2. And dividing by the same thing, which means dividing by 7 over 2. So that's multiplying by 2 over 2 over 7. Minus, what's this guy? 3 over 2 plus 1. Isn't it 5 over 2? 5 over 2, right? Dividing by 5 over 2 is the same as multiplying by 2 over 5. But there is a 2 outside, so multiplying 2 by 2 over 5 is the same as having 4 over 5. U to power 5 over 2, right? U to power 5 over 2, correct? Plus, this is 3 halves, so u to power 3 halves. And this is dividing by 3 halves is the same as multiplying by 2/3, plus the constant of integration. All right, last step. Let's replace what u means for us. And what did u mean? It meant 1 plus x cubed, right? 1 plus x cubed. So that becomes 2 over 7, the u, which is 1 plus x cubed, to power 7 over 2, minus 4 over 5, 1 plus x cubed is just replacement at this point because we finished the integration part, right? We finished the integration part. Plus 2 over 3, 1 plus x cubed to power 3 over 2 plus that constant of integration. Very good. So if you would like to differentiate this to check your work, you should get this as an integrand. Sorry, you should get this integrand as the derivative of this function. Okay? As such, this is a primitive, and this is the most general primitive for that function. All right, moving on to the next concept. It's the substitution rule for definite integrals. If g prime, for definite integrals this time, right? Definite means the bounds are defined. They are bounds. It's not just primitive. It's we're finding a region in some sense, the area of a region, right? The net area. If g prime is a continuous function on a closed and bounded interval AB, and if f is continuous on the range of the function g, then the following happens. The integral from a to b of that guy is equal to the integral of f of u du, but now the bounds are not b and a anymore, because look, x here is bounded below by a and bounded above by b, right? But now we're doing transformation. We're doing a u substitution. This is the substitution formula, remember? That we learned above, but without the bounds at the time. Now, if you plug in bounds here, a and b, the bounds here are going to be g of the lower bound a as a lower bound. So the lower bound remains a lower bound. So instead of a, I'm going to have g of a. And instead of b, I'm going to have a g of b. Okay, so the lower bound a becomes g of a, and the lower bound b becomes g of b. Okay, and what's g of a, what's g of b? Is the choice of the u, it's the choice of the u, the function, evaluated at this lower bound and evaluated at the upper bound, right? Okay. Let's prove this theorem. Let's just read it. Let f be an antiderivative of f. So let capital F be a primitive function of little f. This little f here, right? And because f is continuous, I can do so by the fundamental theorem of calculus part 2. Then, by the substitution rule, we know that f of g of x is a primitive function of this integrand. Correct? We learned this in the previous part. So by part 1 of the fundamental theorem of calculus, what is this then? What is this left-hand side? Well, since we know that f of g of x is a primitive function of this guy, then by the fundamental theorem of calculus, I'm going to get this guy evaluated at the upper bound minus this guy, primitive, evaluated at the lower bound. So I get this. Correct? On the other hand, about this right-hand side, well, by the fundamental theorem of calculus part 1, we also have that this right-hand side is equal to, what's a primitive of f of u? If you think about the variable now being u. Well, the primitive of a primitive of f of u is capital F of u, since we're thinking about little f as being a primitive of f, right? So we get f of u evaluated between g of a and g of b. And what is that? This is f of gb minus f of ga. So you take u, replace it by g of b, and you take u, replace it by g of a. You get exactly this. You get this, which is exactly that. At the end of the day, these two, because this guy is equal to this piece, right? And this guy, which is the same, is equal to this piece. Correct? So these two green things must be the same because they equal that guy, which is exactly this guy, right? So all these green parts are the same. As such, those two are the same, and this is the conclusion of the theorem. See it? This is the conclusion of the theorem. All right, let's do some problems. Let's do some problems here. So let's evaluate part 1, the integral from 0 to 4 square root of 2x plus 1 dx. Okay, I think we did this before. I think we did this above. And we did it in 2 ways. What did we find at the time? Oh, right there. You see this? Primitive of square root of 2x plus 1 dx, we found it to be this guy, right? Correct? We found it to be this guy. So, and we did it in 2 ways, if you remember. Alright, I'm gonna ignore what we did. I'm gonna pretend like we didn't do it. I'm gonna come back to it shortly to make a certain point. Let's pretend we didn't do it, and let's start from scratch. Let u be 2x plus 1, and as such the differential of u would be 2 dx, correct? Which means dx, I'm gonna do it quickly because we've done this exact work before. So half of du is dx, right? Then this can be thought of as, in terms of what goes here, is the square root of u, right, as usual, dx, which is half du. But the question is what goes here? Question is what goes here, and based on the substitution rule for definite integrals, that theorem that we just talked about, what goes here is g of a, g of the lower bound. So the lower bound goes to the lower bound, and the upper bound goes to the upper bound via the transformation g, which is the substitution that we just made. So who's the substitution here? It's the function 2x plus 1. That's g of x. That's g of x, correct? So what's going to happen then at the upper bound and lower bound? The lower bound is going to go to the lower bound. So when x is 0, how much is u? Because now I'm integrating with respect to u, right? As we said, here it's going to be g of 0, right? And that's g of x. That's g of x. G of 0, what? Replace x by 0, what do you get? 2 times 0 plus 1. What's 2 times 0 plus 1? It's 1, right? It's 1, correct? So when x is 0, g of x, which is u, is 1. Now when x is 4, g of 4, which is u, right? U of 4 is 2 times 4, which is 8 plus 1, so 9. Agree with that? Okay. This is equal to 1/2 the definite integral from 1 to 9, u to power half. Square root of u is 1, u to power half, right? Du. And if you integrate this, we've integrated this before, so this is u to power 3/2 divided by 3/2. Agree? Between 1 and 9, right? Between 1 and 9. Okay. And dividing by 3/2 is the same as multiplying by 2/3, so I'm gonna get, if you multiply by 2/3, the 2 and the 2 are gonna cancel, we only get 1/3, u 3/2 between 1 and 9, right? Okay, now we're gonna evaluate this at the upper bound, and we're gonna subtract its evaluation at the lower bound. So what do we get then? 1/3 u to power 3/2 evaluated at 9, which means 9 to power 3/2, right? Minus u to power 3/2 evaluated at 1 is 1 to power 3/2. Yes? And this is the same as, this is simply 1. And how about this? What's 9 to power 3 over 2? Well, 9 to power half is 3, so this becomes 3 cubed, right? This becomes, one more time, this is the same as the square root of 9, the whole thing is cubed. Square root of 9 is 3, 3 cubed is 27. This is 27 then. Okay, so that's 1/3 times 27 minus 1, which is 26 over 3. Make sense? All right. So this definite integral, which means what? Geometrically, it means the region bounded by the curve y equals square root of x, 2x plus 1, the x-axis, and the two vertical lines x equals 0 and x equals 4. It happens that this area, just described, this net area is, the net area of that region is 26 over 3. Okay? And this function is certainly above the x-axis, right? Okay. So this is then the area under the curve, square root of 2x plus 1 between 0 and 4. Okay. All right. Let me show you a different way to do it without appealing to the substitution rule for definite integrals. Remember at the time we integrated that, we integrated this integral. We found a primitive for it, and it was this. And it was this. I'm gonna copy that result. I'm not gonna take c because I can take c constant. I have a definite integral now, right? I'm gonna copy this result, and what I'm gonna do is the following. So I wanted to integrate this guy between 0 and 4. One way to do it, as we said, by using the substitution rule for definite integrals, okay, which means the bounds are gonna change when we do this substitution, this transformation. Or what I can do is I can do it in steps. I can ignore those guys, those bounds. I can find a primitive for square root of 2x plus 1, which we found above, right? I just copied it. So we can find the primitive for this and then apply the fundamental theorem of calculus, which means take the primitive evaluated at the upper bound and subtract the primitive evaluated at the lower bound, 0. Okay? So what I'm going to say here is, so this is an alternative approach, right? So alternatively, since we found earlier that this guy, right? Just zoom out. So this guy is a primitive function, so an antiderivative of the integrand, which is square root of 2x plus 1, right? What's the integrand here again? It's the square root of 2x plus 1. We use the fundamental theorem of calculus part 1 to get that this guy between 0 and 4, right, square root of 2x plus 1 dx is equal to that guy, primitive, so 1/3 2x plus 1 square root of 2x plus 1 in between 0 and 4, right? So you can go all the way to the primitive of this guy and then apply the fundamental theorem of calculus, part 1, to evaluate this at the upper, and you subtract the result if you evaluate this at the lower bound, correct? Or you can use the previous method, which has to do with the substitution rule for definite integral, this one. Sounds good? And obviously this is going to also give you the same answer. Let's see. That's 1/3 times, I'm going to take this guy evaluated at the upper bound. Let's do it. 2 times 4, right? 2 times 4 plus 1 times the square root of 2 times 4 plus 1. Same thing, right? Minus, evaluate this at the lower bound. And what's that evaluation? 2 times 0 plus 1, square root of 2 times 0 plus 1. Yes? How much is this? That's 1/3 times, that's 8 plus 1, so 9 times the square root of 9, so 3, minus, that's 1, and that's 1, minus 1. So that's 1/3 times 26, which is 26 over 3, which is exactly what we found above, right? Which is exactly what we found above. So you have two approaches to evaluate integrals that require U substitution. Either you do the U substitution and you appeal to the substitution rule for definite integrals, which means you transform the bounds as well, right, in the process, or you just ignore the bounds for the moment, you find an antiderivative of that integrand, and then you apply the fundamental theorem of calculus part 1 to do the evaluation. Okay, all right, let's do one more. Part 2. How about primitive or definite integral this time? 1 to 2 dx 3 minus 5x squared. Okay. All right. Please stop the video. Again, every time I'm not gonna repeat myself. Every time I give a problem, stop the video and do it on your own, because it doesn't make sense to watch it without learning from mistakes. So let u be 3 minus 5x. As such, du is equal to minus 5 dx, right? It's u prime, which is minus 5 times dx. So that thing is equal to then, oops. So this is equal to the integral. Downstairs is u squared, correct? Upstairs, dx. What's dx in terms of du? How about we write it here? What's dx in terms of du? Doesn't it mean minus 1/5 du? Right? So I'm gonna take everything down. So right, I'm talking about this. So one more time, I want to write everything in terms of u here, right? Downstairs is u squared, no problem, because that's my choice of u. Now dx upstairs, what's dx in terms of u? Or what's dx in terms of u and du? Well, dx is minus 1/5 du. Why? Because minus 5 dx is du. So dx is minus 1/5 du. So minus 1/5 du, right? Correct? Now the bounds. Who sits here and who sits here? Well, based on the substitution rule for definite integral, who's gonna sit here is what used to sit here, but you have to apply this recipe for it now. You're gonna apply this transformation. If x is 1, here I'm talking about x being at the lower bound 1. The question is, what's the lowest bound for u, right? Where does u go if x goes to 1? Well, if x goes to 1, u goes to -2, right? Agree with that? So one more time. If x goes to its lowest bound, which is 1, u is gonna go, I'm gonna replace x by 1. So this becomes 3 minus 5 times 1. 5 times 1 is 5. 3 minus 5 is -2, right? Now, if x goes to its upper bound, 2, right? X goes to its upper bound 2. U, now X is going to go to 2. U is going to go to 3 minus 10, which is minus 8. Do you agree with that? Agree with that? One more time. If X is 2, minus 5 times 2 is minus, oh, I did a mistake, minus 7, right? So again, if X is 2, minus 5 times 2 is minus 10, minus 10 plus 3 is minus 7. Okay. All right. And that's minus 1/5 integral minus 2 minus 7, from minus 2 to minus 7. Du over u squared, which is minus 1 over 5, integral from minus 2 to minus 7, u to power negative 2 du, right? U to power negative 2 du. By the way, here I hope you realize that when x reaches its lowest bound, u is reaching its upper bound, because negative 2 is bigger than minus 7, right? And this is reasonable because the function is decreasing, right? Look at the function, the transformation function, the substitution. 3 minus 5x, isn't it a decreasing line? So the lowest is gonna becomes the largest, and the largest is gonna turns out to be the lowest, right? Correct? But we don't flip. If you wanna flip, you have to pay a price minus, because what the theorem tells us, if you remember, what the theorem tells us, they have to go straight, right? In some sense. So meaning the upper is sitting as the upper, even though this may not be the upper, like we saw, and the lowest goes to that lowest location. Okay, at least the way it's written. Okay, but if g is a decreasing function, that guy g of b may be smaller than g of a, which is fine. Okay. All right, so where are we? So we're here. Okay, this is equal to I mean, we can integrate, so minus 1 over 5. Let's integrate u to power negative 2. We're still talking about that guy, primitive. Let me write it for you again. So primitive of bullet to power negative 2 d bullet, right? This is the bullet to power negative 2 plus 1 over negative 2 plus 1, correct? Plus c. Makes sense? So obviously this can be any number. This minus 2 instead of minus 2, this can be replaced by any number different than minus 1. Okay. All right. So here I get the bullet to power minus 1. Minus 2 plus 1 is minus 1, right? And that guy minus 1 downstairs. Dividing by minus 1 is the same as multiplying by minus 1, which means take the opposite of the bullet, which is u, right? Bullet is u, to power negative 1. Agree with that? Check, I mean, you can check the work. You differentiate this with respect to u, you get minus 1 times minus, which means plus 1. U to power negative 1 minus 1, so u to power negative 2. You get back this. So this is how you check your work if you want. Very good. And this is going to be taken between minus 2 and minus 7, right? I'm going to take the constant to be 0 because I'm going to take, this is a definite integral here. Okay, because they're going to cancel. If you choose something else, they're going to cancel, as we talked in the previous section. Okay, then what? The minus with the minus, they're gone. So 1/5. U to power negative 1 means 1 over u, right? This means 1 over u. So that's going to be 1 over negative 7. So minus 1 over 7 minus u to power negative 1, replacing u by minus 2. U to power negative 1 means 1 over u. replace u by -2, it means 1 over -u, right? -2. Okay. So again, just to make it clear, this guy is 1 over u. Okay. And we talked about that minus with this minus, that's gonna be a plus, correct? This is why you see a plus here. Very good. Okay, this is 1 over 5, negative 1 over 7 plus half, right? 1 over 5 times, how about the same denominator here, which is 14? 14, 7 times 2. So minus 2 upstairs plus 7. Okay. And 7 minus 2 is 5. Divide by 5 is 1. So that's 1 over 14. Okay. I was expecting a positive number because I'm integrating. You see this function 1 over, the function is 1 over, right? 1 over 3 minus 5x to the power 2. This is a positive function, so this function is above the x-axis, right? If this is the x-axis, this function is above it, and I'm integrating between 1 and 2, so I'm talking about a region like this, right? Certainly this is the net area here is positive because there is no piece of this function below the x-axis, so this is certainly a positive number. This area here is a positive thing. Correct? All right. Excellent. Let's keep going. Okay, the last concepts in this section is a theorem. Let's read it. Integrals of symmetric functions. Suppose f is a continuous function on this set minus AA. It's a symmetric set. Minus AA. If f is an even function, which means algebraically it means f of negative x is equal to f of x for all x in the domain, so for all x here, and geometrically it means that the function is symmetric with respect to the y-axis. Okay, it doesn't have to be above the x-axis all the time, but it's symmetric with respect to the y-axis. Then the integral from minus a to a fx dx is twice the integral from 0 to a fx dx. So intuitively, geometrically, if you want to think about f as being a non-negative function, so take f to be a function above the x-axis, since it's even, it has to be symmetric with respect to the y-axis. So what we're saying here is the area under the graph and above the x-axis, so this blue shaded region, is twice a piece of it, right? I mean, it's believable, at least when you consider f to be non-negative. Now, if f is odd, which means f of negative x is minus f of x for all x in the domain here, we're talking about minus AA. So if f is odd, which means this happens, then this integral from minus a to a fx dx is 0. And let me convince you, at least when the function f is at least something like this, right? It's symmetric with respect to the origin, because any odd function is symmetric with respect to the origin, correct? This is the geometric characterization of it. So it's something like this. And if you integrate between minus a and a, the net area, this is the net area, remember? Net area, which means you add up all the region above the x-axis and you subtract from that the sum of the region, or the area of the region below the x-axis and above the function. So in this case, you're talking about this region and this region. So you're going to do this minus this. But they are the same regions, the same area. Correct? That guy and that guy are the same because of symmetry. The function is symmetric with respect to the origin. So that guy minus itself is 0. Okay? All right, let's do it algebraically using substitution. So the proof, the integral from minus a to a fx dx, I can split it as, previous result, you can go minus a to 0 and then 0 to a, right? You can split it, stop at 0 and continue from 0 onward to a. And that guy, if you swap the bounds, you pay a price minus, right? If you swap the bounds, you pay price minus. So we get this. And we keep this as itself. I'm just copying it. If you call this guy I, with that minus sign, if you call this whole thing I, so I get to this point. So that's I. How about I use substitution as follows? Replace x by negative x. Replace x by negative u. Okay, so replace x by negative u, or replace negative x by u. So call u to be negative x. As such, every time you see x, it's gonna be negative u, right? So that guy is gonna be negative u, and that guy is gonna be negative u. Correct? So du is negative dx, or dx is negative du. So this guy becomes negative du. It's right there. And how about the bounds now? When x is 0, how much is u? When x is 0, u is also 0, right? So we go to 0. When x is negative a, when x is negative a, when x is negative a, how much is u? Well, u is the opposite of x. If x is negative a, u is the opposite of a, so it has to be a. Correct? All right, and then this minus talks to this minus. They cancel each other. We get a plus. So this becomes the integral from 0 to a f of negative u du. Right? And as such, go back to this integral that we had, this guy, is equal to I. What's I now? It's this guy. So I'm copying. This is I plus this piece. Agree? Okay, I'm calling this equation the musical note equation. I'm gonna refer to it shortly. Now for part one in the theorem, what's part one? I'm assuming that f is even, which means f of negative x is f of x. So if you assume that f is even, which means f of negative x is equal to f of x, but x is a dummy letter. I can call it u, I can call it t, whatever you want. So this is true, right? So equation musical note becomes the integral from minus a to a f of x dx is equal to this guy, but we just said f is even, so f of u is f of negative u. So instead of f of negative u, you can write f of u plus the integral from 0 to a f of x dx. Right? And look at this. Integral from 0 to a f of u du plus integral from 0 to a f of x dx. This is, forget about the name of the variable. Think about this as star or something. Right? Isn't that the same star? Isn't that the same star here? So I can call this star whatever I want. I can call this star whatever I want. Likewise here. This guy and this guy are the same. I can call those guys whatever I want. How about calling all of them x, or calling all of them t? So this becomes primitive 0 to a, or not primitive, definite integral from 0 to a f of t dt plus integral from 0 to a f of t dt. So it's twice that thing. Right? So it's twice that thing as desired. If you assume now that for part 2, if you assume that the function is odd, which means f of negative u, right? This guy f of negative u is negative f of u. Equation musical note now becomes the integral from minus a to a fx dx equals minus the integral from 0 a f of u du plus the integral from 0 to a f of u du, right? See this? And same story. That guy is a dummy letter, right? So it looks like negative primitive integral from 0 to a f of t dt plus integral 0 to a f of t dt. So isn't that the same? You're subtracting the same thing from itself. So we get 0. Okay, so we get this. All right. let's do one problem here. So let's calculate the following. The integral from minus 2 to 2 x to the power 6 plus 1 dx. Sure, we can we can find a primitive for this function and use the fundamental theorem of calculus to evaluate it at the upper bound and then subtract its evaluation at the lower bound, right? We can do that, but this would be too much since we already have a result. Since we have a result over here, right? If you integrate over a symmetrical domain from minus a to a, if you integrate an even function, so it would be twice the integral from 0 to a fx dx, and if you integrate an odd function, then you would get a result that's 0, right? So this is a symmetrical domain, so we don't have to integrate all the way from minus 2 to 2. We can split the work. We can cut the work in half if the function is even, and this is an even function, right? You agree with that? This is an even function. Why? Because it's the sum of two even functions. This is even. Since f of negative x is equal to f of x for all x. Correct? For all x. Agree with that? As such, what do we get? Based on the previous result, this is twice the integral from 0 to 2 x6 plus 1 dx. You agree with that? So we cut the work in half in some sense. Okay? And this is equal to 2 times the integral, not the integral, I'm going to integrate. So 2 times, let's find a primitive of x6 plus 1. It's x7 over 7 plus x, right? If you integrate x6, you get x7 over 7, and if you integrate 1, you get x. And this is between 0 and 2. Correct? So that would be twice. Let's evaluate this at the upper bound. So 2 to the power 7 over 7 plus 2, correct? So one more time. That guy evaluated at 2 is 2 to the power 7 over 7 plus 2 minus 0, right? If you evaluate this at the lower bound 0, so everything here is 0. So I'm not going to copy it. So we get this. Agree? And whatever this answer is, I'm going to just leave it as is. I'm not going to find the actual answer. Okay? The last problem, I'm going to integrate between minus 1 and 1 tangent x divided by 1 plus x squared plus x to the power 4 dx. Okay? Again, I'm still integrating over a symmetrical domain, minus 1 to 1. So if I'm lucky, I get a function that's odd, so I don't have to integrate this whole thing. I don't even know how to integrate this. So my hope is that this is an odd function, and if it is an odd function, based on the discussion we just had here, then that's going to turn out to be a 0. That's going to turn out to be 0. Correct? Well, by the way, this function is continuous between minus 1 and 1, right? This function is continuous between minus 1 and 1. This guy downstairs is never 0. Well, why do I need to check that this is continuous between minus 1 and 1? Because, I mean, look at the theorem. It's supposing that the function is continuous on this symmetrical domain, right? So, in the first case, it was immediate. I didn't even have to talk about it because this is a polynomial which is continuous everywhere, in particular between minus 2 and 2 at that time, right? Here, tangent x over 1 plus x squared over plus x squared. This whole thing is continuous. On minus 1, 1. Why? This function is continuous wherever it's defined, right? Because it's a quotient between a trig function and a polynomial. Well, this guy downstairs is always bigger than or equal to 1, because x squared is at least 0 and x4 is at least 0, so the guy downstairs is at least 1. So this guy downstairs is never 0. The only problem is, where is tangent defined? Where is tangent defined? Well, tangent is defined as long as cosine is not 0, because tangent is sine over cosine. So for the tangent to be defined, I need cosine not to be 0, and cosine is not 0 if and only if x is not equal to pi over 2 plus an integer multiple of pi, right? Where k is an integer. Correct? So this is from trig. So tangent is not defined at those points. And what are we talking about here? Minus 1, 1. Minus 1, 1. Does minus 1, 1 contain any of these 2 points? Does minus 1, 1 contain any of those points? Well, let's see. If k is 1, what happens? If k is 1, actually if k is 0, a bad point would be pi over 2, right? We get, if k is 0, we get pi over 2, right? And pi is approximately 3.14, and 3.14 is bigger than 1. 3.14 over 2 is bigger than 1, right? It's bigger than 1.5. So that bad point, when k is 0, is bigger than 1. Agree? Which is beyond this upper bound of this symmetrical domain. How about, so it looks like when k is 0, I'm outside, I mean the bad point becomes outside of the set. And when k is 1, you're moving in the positive direction of that upper bound 1, right? You're increasing. So when k is 1, you get pi over 2 plus pi. So you're way beyond 1, and the more you increase k, the more you are to the right of 1. Correct? Okay. How about when k is negative 1? How about when k is equal to negative 1, which is the previous integer, because k can only be integers. The previous integer before 0 is negative 1. So that means x cannot be pi over 2 minus pi, correct? Pi over 2 minus pi. And what's pi over 2 minus pi? Is negative pi over 2, correct? And negative pi over 2, this guy is less than negative 1. Why? Because, I mean, it's the same reason. If you multiply both sides by negative 1, you have to reverse the inequality sign. So minus pi over 2 is less than negative 1. So we get this, right? Okay. All right, so long story short, the bad points are outside the set. Okay? The bad points that make the function not continuous are outside the set, because the first one occurs after 1 is when k is 0, and the first one before negative 1 occurs when k is negative 1. So, and then all the rest become smaller than that guy. When k is a negative integer, all the bad points are less than minus pi over 2, which is in turn less than minus 1. And when k is a positive integer, all the bad points become away from pi over 2, which is in turn away from 1. So all in all, all the bad points where the function is discontinuous are outside the set minus 1, 1, the set of integration here. And on the other hand, so now that the function is continuous on minus 1, 1, it's not hard to see that this function is actually an odd function, right? Because tangent is an odd, and the guy downstairs is even. So the quotient between an odd function and an even function is an odd function. So this is an odd function. So odd. As such, because of the previous result, and what do I mean by previous result? It's that one that I just talked about few seconds ago, this one. So since f is odd, you're integrating between minus a and a of continuous function. That's continuous function. We made the case. So this is going to be 0 at the end of the day. This is going to be 0. We don't even have to go through the trouble of finding a primitive of this. Okay? We don't have to go through the trouble of finding a primitive of this integrand. As a matter of fact, I have no idea how to find a primitive of this. So thank God it's an odd function integrated over this symmetrical set, and it's continuous there, right? As such, the previous theorem tells us that this is this definite integral is 0. All right, so this ends this section.